Welcome to my YouTube channel A-Tech Learning, where the magic of data come to life. I am Aruna and I get into the world of data science. If you are here, don't forget to hit that subscribe button to stay updated on all things about data science. t-SNE is one of the non-linear dimensionality reduction technique, where it helps to explore high-dimensional data in a low-dimensional space by preserving the local structure. Non-linear dimensionality reduction technique, meaning we have a bunch of data points which is a non-linear in nature. That means we cannot separate those data points with a straight line. So when we are trying to reduce the dimension of such data points, it is known as non-linear dimensionality reduction technique. t-SNE is one such method which helps to reduce the dimension of such data points to the low dimension space. t-SNE is widely used to visualize high-dimensional data sets in a low-dimensional space, that is, 2 or 3-dimensional space. This is particularly useful for understanding the structure of the data, identifying the clusters, and revealing patterns that might not be apparent in the raw data. t-SNE can also help to identify groups, trends, or outliers in the data. By visualizing data in lower dimensions, we can easily understand which features contribute most to the separation of data points. This insight can be valuable for feature selection. In domains like genetics, neuroscience, and natural language processing, data sets often have a large number of features. t-SNE helps researchers and data scientists understand the relationships and the structure within these complex data sets. Now let's understand how t-SNE works. t-SNE works by calculating the similarity between data points in high dimensional space and then trying to map those similarities in the lower dimension space. It does this using probability distributions. The algorithm tries to minimize the difference between these distributions, effectively pulling similar points together and pushing dissimilar points apart. In brief, consider an iris data which is non-linear in nature, and it has 4 features, that is sepal length, sepal width, petal length, and petal width, and 3 classes, that is setosa, versicolor, and virginica. So these are the 3 species of iris. This is how it looks in a pairwise plot. So it is a 4-dimensional data. So let's convert it into 2-dimensional data using t-SNE. So this is a result of iris data after converting to 2-dimensional data. Notice that we now have 2 dimensions, dimension 1 and dimension 2, where we have reduced the 4 features into just 2, with clear clusters of iris classes. Hola! We will now understand step by step how t-SNE converted high dimensional data to a low dimension. Step 1, we need to calculate the probability distribution for every pair of points in a high dimensional space. So the probability distribution helps us to understand for a given data point x, what is the probability that it chooses the point y. If x and y are similar points, then the probability is high. If it is dissimilar points, then the probability is low. So this helps to keep the similar points together. Step 2, we need to project the high dimensional points to a low dimensional space. When we reduce 2-dimensional to 1 dimension, we lose y-axis. That means we are losing some properties of the data. We don't want this to happen. Hence, in the next step, we need to calculate the probability distribution for every pair of points in the low dimension space. Now, we have 2 probabilities. One is the probability in a high dimension space and the probability in a low dimension space. Once we have the probabilities in both high dimension and low dimension, our task is to pull the similar points together and push dissimilar points apart, thus maintaining the local structure of the data points. Hence, we use KL divergence to perform this task. So, KL divergence helps in minimizing the distance between the 2 probabilities by keeping P as constant and moving the Q probabilities towards P probability. Thus, after applying KL divergence, we get approximate same probability distribution in low dimension as in I dimension. Hence, we are able to preserve local structure of the data points by keeping all similar points together. t-SNE uses student's t-distribution to calculate probability distribution between points, and since it mainly focuses on preserving local structure of data points concentrating on the neighboring points, it is named as t-SNE, which means t-distributed stochastic neighbor embedding. For a dataset with n elements, t-SNE runs in big O of n square time and requires big O of n square space. The disadvantage of t-SNE is it is less concentrated on the global structure, which can sometimes lead to misleading interpretations of clusters or relationships in the lower dimensional visualizations. To wrap up, t-SNE or t-distributed stochastic neighbor embedding is one of the non-linear dimensionality reduction technique where it helps to visualize high-dimensional data. It reduces complex data sets to 2D or 3D while preserving local structures, making it easier to identify clusters, patterns, and trends. t-SNE uses probability distribution to calculate the similarity between points in high dimensional space and then map those similarities in a lower dimensional space. t-SNE uses KL divergence to reduce the distance between probabilities, thus helps in preserving local structure of the data. Limitation: t-SNE focuses on local relationships, sometimes missing the bigger global picture. That is all for today. Thank you so much for watching this video.